Hi students, welcome to my channel. In today's session, I am going to explain what is crystal field theory, why this theory arose. This theory arose to overcome the limitations of valence bond theory. Already we know that valence bond theory is explained based on the overlap of metal ligand orbitals. That theory does not explain the interpretation of magnetic data, and based on the strong field and weak field, the structures and hybridization everything is different. Does not explained by valence bond theory. So to overcome that limitations, crystal field theory arose. Here, this theory explains based on the electrostatic interactions. So first point, crystal field theory arose, or this theory based on the electrostatic interactions. Electrostatic interactions between metal and ligand electrons. Metal and ligand electrons. Metal also has electrons, ligands also has electrons. Due to interaction between these metal and ligands, ionic bond is formed. See here, metal has positive charge and ligand has negative charge because it has negative ligand and neutral ligand. Both are donating electrons. So negative poles are there. So because of this, now ionic bond is formed. So what crystal field theory is explained, when metal and ligand approach each other, it forms ionic bond. It forms ionic bond. So that's why electrostatic interactions takes place between metal orbitals and ligand orbitals. Next, when ligand approaches metal, see students, metal has electrons, right? Metal has electrons. When ligand also has electrons, right? Metal in outer shell it has electrons, ligand also in outer shell it has electrons. When this ligand electrons approaching metal, so here first electrons are there, right? Then cation is there present inside the nucleus. So when ligand approach the metal ion, there is a electron-electron repulsion takes place. Electron-electron repulsion. Electron-electron repulsion. Where electron-electron repulsion takes place? Between metal and ligand. Clear students? Between metal and ligand, electron-electron repulsions takes place. To avoid this, what happens when ligand approach metal ion? So repulsion takes place. When repulsion takes place means then degeneracy of metal orbital is destroyed. See here, already we know that here what type of metal involved? It is a d block elements. That is d block elements, metals only involved. First row transition metals. So d block element means it has 5 orbitals. D subshell has 5 orbitals. See students, D subshell has 5 orbitals. This is known as degenerate orbital. This orbital is known as degenerate orbital. What is the meaning for degenerate orbitals? That orbitals has equal energy. These 5 orbitals has equal energy. That is degenerate orbitals. So this one for free metal ion. This degenerate orbital is for free metal ion. Free metal ion. In free metal ion, that means without ligand, so it has equal energy. But when ligand approaches, what happens? Electron-electron repulsion takes place. That's why degeneracy of this orbital is destroying. Clear students? When ligand approaches this metal orbital, degeneracy is destroyed. So how it is destroyed means this energy is lifted. The equal energy of degenerate orbital is lifted. So it lifted means, see now this energy is lifted. This is non-degenerate orbitals or average energy in crystal field. What is crystal field? When ligand approaches the metal ion. Without that, it is not a crystal field. It is a free metal ion. It has equal energy. After approaching of ligand, now the energy of this 5 orbital is changed. So this one is for average energy. This is average energy in crystal field. Okay, students. Next, so what happens here to attain the stability or to maintain the stability? Now this orbitals, this non-degenerate 5 orbital is splitted into two sets. This orbitals splitted into two sets. See here, students, this one and here. This 5 splitted into 3 and 2. So this is known as T2G and this is EG. So now non-degenerate orbitals split into two sets, T2G level and EG level. So this gap is known as splitting energy gap. This gap is known as splitting energy and is mentioned by delta. Here two times are based on the complexes we will represent del O and del T. Del O for octahedral complexes, del T for tetrahedral complexes. Clear, students? So why splitting takes place in metal orbitals? When ligand approaches, what happens? The degeneracy of 5 orbital is changed. Okay, it's destroyed and the energy is lifted. So after that, it splits into two. Clear, students? T2G set and EG set. And this center point is known as barycenter. Clear, students? And we can calculate the values also. Here, two states are there, right? So the value is plus 3 by 5 delta. And here, three boxes are there. So it is minus 2 by 5 delta. So 5 means out of 5 orbitals, here minus 2 by 5 its value. And here out of 5 orbitals, two boxes are here. So 3 by 5. So one clue is there, that is opposite of boxes. Here how many boxes? And opposite value 3. Here 2 boxes, 3. Here 3 boxes, here 2. Why this plus and why this one is minus means, if you consider this as an axis, students, this is above the axis plus, this is minus. In graph we plot like above y-axis, that is above the origin it's plus value, below the origin is the minus value. Like that it's there. If you find the answer for this fraction, you will get this one as plus 0.6 delta O for octahedral complexes and this one minus 0.4 delta value. If it is octahedral means O. Clear, students? So this value plus 0.6 and minus 0.4. Clear, students? This is the value. Next, that splitting is based on the ligands, 4 factors. Generally, the splitting of d orbitals, when ligand approaches, the splitting based on 4 factors. We will discuss what are the 4 factors. See, first point. Factors or splitting depends on generally 4 factors it depends on. First one, based on ligands, whether it's a strong field ligand or weak field ligand. And second, it depends upon the geometry of complex. Splitting means this gap, students. Okay, this splitting depends on these 4 factors. Geometry of complex and charge on central metal ion. charge on central metal ion and number of d electrons involved. Based on these four factors, the splitting may change. Okay students, so first in today session I am going to explain first three. Okay students, let's discuss. See now, first based on ligands. So first point, based on ligands. Two types of ligands are there students, strong field ligand and weak field ligand. If the ligand is strong field, ligand and for weak field. Okay, first in strong field ligand, before approaching the ligand, metal has 5 orbitals. Right students, after the approaching of metal, what happens? It moves to non-degeneracy level. Right? Here it splits into two. One is T2G set and another is EG set. Right students? This is T2G and EG set. So here, what is the difference between these two? Here mainly, if the ligand is strong field, means all the electrons first enter into T2G level students. This is the main point. This is very important point as well as string students. If the ligand is strong, means all the electrons first in present in T2G level. That means pairing occurs. 3 orbitals are, that means 6 electrons can occupy. So first 6 electrons occupied here, then remaining electron will go for EG level. Clear students? This is the first point. So here pairing takes place. Pairing takes place in which set? In T2G level. Okay students, in T2G level pairing takes place. Next one. What is one more difference is there? That means the splitting energy is there students between these two sets. The splitting energy is large. The splitting energy is large for strong field ligand. That means delta O. That means O represents for octahedral. So delta O is greater than P, than pairing. Okay students. So for pairing it requires more energy, right students? So that's why the electron is not preferring this EG level, because it requires more energy. That's why electrons first filled in these levels, then go for EG level. Clear students? Because here splitting is large. The delta naught value is large for strong field ligand. That means splitting is large. Clear? And next, for weak field ligand. For weak field ligand, see here, same thing. Here it is free metal ion. This is free metal ion state. Once ligand approach, what happens? This degeneracy is lifted. Now it's shifted to non-degenerate level. Here splitting of electrons takes place. Okay students, see here it splits into two levels. This is T2G level, this is EG level. Here see students, splitting is very less than this one. In strong field ligand, splitting is more. In weak field ligand, splitting is less. So here splitting is less. That's why electron can easily move to EG level. When splitting is large means the electron will not move to EG level. Splitting is less means electrons can easily move to EG level. That's why here when weak field ligands are there, no pairing. When weak field ligands are there, no pairing in T2G level. And delta P is less than, that means splitting is less. Clear students? This is the difference between strong field ligand and weak field ligand. That value here value is same. Here it is minus 0.4, here plus 0.6. Here also same, minus 0.4 plus 0.6. But the difference is this one. Pairing takes place in T2G level for strong field. Then extra electrons move to EG level. When weak field ligands are there, first all 5 orbitals are filled by single electron. Then excess electron comes to T2G level. So this is the important difference between strong field and weak field. So this explanation is not given in VV theory. That is the limitation of the theory. Clear students? Next one, geometry of complex. Before that, you should know the charge on central metal ion. What happens when charge differ in the central metal ion? So second factor, factor number 2. That is factor 2. What is second factor? Charge on central metal ion. Charge on central metal ion. Here I am giving trick students for that. So see, first higher charge on central metal ion. Higher charge on central metal ion means delta naught value will be more. Okay, that means splitting will be more, students. Delta naught value will be more means what is the meaning? Delta naught more means what happens? Splitting is large. Okay, students. When splitting large means what happens, students? Pairing takes place, right? Pairing in T2G level. Clear? Then most of the complexes are low spin complexes. When pairing takes place in T2G level means the complexes are low spin complexes, as well as most of the complexes are diamagnetic. Clear, students? It is just opposite for chargeless. Here best example is, for this factor, best example, see students, this cobalt plus 3 complex, cobalt NH3 6 plus 3 is low spin complex and diamagnetic. It is low spin and diamagnetic. And CONH3 6 plus 2, CONH3 6 plus 2 is high spin complex and paramagnetic. So this is explained based on this concept, students. These two complexes explained based on this charge and central metal ion. See here, cobalt is +3 here, cobalt is +2 here. That's why more charge means it leads to low spin. Why it is low spin? Because splitting value is more. Delta O value is greater than pairing value. That's why pairing takes place in T2G level. So there is no unpaired electron. So it leads to diamagnetic. But here splitting is less. So electrons easily enter into EG level. So it leads to unpaired electrons and paramagnetic. Okay students. So here I explained two factors based on the crystal field when ligand approaches. Clear students? I hope it will be useful for you. If you are not understanding, watch this video again and practice by yourselves. Thank you for watching. If you like this video, please give thumbs up, share and subscribe to my channel.